Okay, so now that you have the divided difference table, okay, so let's just write this F matrix as F00, F10, F11, Fn0, Fn1, all the way up to Fnn. Okay. So I'm going to talk about how you get how do you use these coefficients in the divided difference table to write down the Newton interpolating polynomial, right? So this is the Newton interpolating polynomial. Right, from the divided difference table. Okay, so there are two main forms of this. So there's the Newton forward divided difference. Okay, and what I mean by that, let me just illustrate this with an example with a degree 3 interpolating polynomial. So it's a0 plus a1 x minus x0. So this is the one we've seen before, plus a2 x minus x0 x minus x1 plus a3 x minus x0 x minus x1 x minus x2. Okay, so where now a0 is f00, a1 is f11, a2 is f22, and a3 is f33, right? So these are the entries, they're the diagonal entries, all right? And it's perhaps a little bit more instructive to see what f00 is, right? So f00 is just this divided difference, f at x0, right? F11 is f x0 x1. This is f x0 x1 x2, and this is f, sorry, little f, f x0 x1 x2 x3. Okay. All right, so that's one way to write down the divided difference table, to use the divided difference table to get a particular form of the Newton interpolating polynomial. There's also what is called the Newton backward divided difference. Okay, where I write P3x as a0 plus a1 x minus x3. So it's called backwards because you use the sort of the entries, it's like corresponding to positions in the backward order. Okay, plus a2 x minus x3 x minus x2, right? Plus a3 x minus x3 x minus x2 x minus x1. So it's called the backward divided difference because these things are ordered in the backward fashion. And then here the relevant entries are f30, right? A1 is f31, A2 is f32, and A3 is f33. So this is the divided difference at x3. This is the divided difference at x2, x3, this is the divided difference at x1, x2, x3, and this is the divided difference at x0, x1, x2, x3. Okay, all right, so in the forward form, you're using the diagonal entries, okay, and in the backward form, you're using the bottom row, okay. But it's important to realize that this is essentially just a different representation of the same interpolating polynomial. But maybe it's like you have a particular reason to prefer. It's like one form over the other. That's sort of application dependent. Okay, but again, the reason why I say the Lagrange form or the Newton form of the interpolating polynomial is that the interpolating polynomial itself is unique, but its representation may be different. And you may prefer one representation over the other because maybe it's conceptually easier to understand, or because it's numerically sort of more efficient from the point of view of evaluation. There are many ways it's like to construct one of these interpolating polynomials. Okay, so in that situation, let me just demonstrate that it gives you the same expression for a particular set of values. Okay, so let's look at an example of both the forward divided difference and the backward divided difference and show that it essentially gives you the same expression. Okay, all right. So let's look at an example. And I'm going to compute the divided difference table associated with this as well. So 0, 1, 2. This is the I, if you will. So x0. Okay. So x0 here is 1, x1 is 2, and x2 is 4. Okay. And f of x0 is going to be 2. F of x1 is going to be 1, and f of x2 is going to be 6. All right, so I'm going to fill in the divided difference, right? So this first order divided difference is this minus this. So 1 minus 2 divided by 2 minus 1. So that's minus 1. Okay, so this divided difference is 6 minus 1. 6 minus 1 divided by 4 minus 2. So it's 5 divided by 2. Okay, and then this divided difference is 5 over 2 minus minus 1. So 5 over 2 minus minus 1 divided by 4 minus 1. 4 minus 1. So that is 7 over 2 divided by 3. So 7 over 6. Okay, so the divided difference matrix is 2, 1, 6, minus 1, 5 over 2, and 7 over 6. So if you recall, if you want to do the forward Newton sort of interpolating polynomial, you look at the diagonal. If you want to look at the backward Newton interpolating polynomial, you look at the bottom row. Okay, so with that in mind, the Newton forward interpolating polynomial is given by P2 of x is 2 plus minus 1 times x minus x0. x0 is 1, x minus 1, plus 7 over 6 times x minus x0, which is 1, x minus x1, which is 2. Okay, all right. And you can check what that is when you expand it out. That is 7 over 6x squared minus 9 over 2x plus 16 over 3. Okay, and then the Newton backward interpolating polynomial, right? P2 of x has the form 6 plus 5 over 2 x minus x2, which is 4, plus 7 over 6 x minus x2 and x minus x1. x1 is 2. Okay, so, and you can check when you expand this again that this is 7 over 6 x2 minus 9 over 2x plus 16 over 3. Okay, so in both cases you get the same interpolating polynomial. It's just that their representation is different. Okay, all right. So let me just stop here for now, and then I'll say something a bit more about the properties of the divided difference table.